next talk is by Abhishek Tiwari on bridging ROS2 with Simulink for model-based design. Come on, guys. Thank you. You guys have become so smart with me, just a cue and you know what to do, right? Thank you. Thank you so much.
Hello, everybody. Good afternoon. So before starting the session, I would like to ask, how many of you have used MATLAB or Simulink? Oh man, that's a huge number. It's good to see people are using our products. So let's start with the topic that I'll be discussing today, which is bridging ROS2 with Simulink for model-based design. So let me introduce myself. I'm Abhishek Tiwari, engineer at MathWorks. And today I'll be discussing mostly about how you can integrate ROS2 with Simulink to design your autonomous systems. Let's get started. Let's go through the agenda first. So today I'll first introduce about what is model-based designing and what is the importance of model-based designing. Then we'll see how we can integrate model-based designing in a ROS environment. After that, we'll go through a case study where I'll be talking about model-based designing for a ground control system that we developed using ROS2. And at last, by the end of the session, you will have a comprehensive understanding of how you can leverage Simulink to design your autonomous system. Let's start with our first agenda. Here the chart shown indicates that when the errors are introduced in our development cycle and when they are detected. So as you can see in the study, most of the issues are introduced in the initial state of the development, but they are found only at the later stages, mainly during test. And some of the issues may even remain in the software and are detected only in the field. The cost of resolving this issue increases as we go later in the cycle. With the model-based designing, you can increase the use of modeling and simulation for your development process and increase the modeling and simulation. So with the help of MATLAB and Simulink, you can design your autonomous systems. You can design our algorithms using Simulink blocks just by dragging and dropping them onto the model. And once you have the model ready, you can simulate it, do the code generation, and test and verify. The best part of this process is you don't need to write a single line of code. Now the question is, how you apply model-based designing in a ROS workflow? So the answer is, we have developed ROS Toolbox for you guys so that you can integrate ROS2 with Simulink and design your autonomous systems. Now the question is, how exactly you do the ROS programming? So we have a huge set of Simulink blocks that you can use for creating publishers, subscribers, services, and action. Not only that, you can use our utility blocks to process images, point cloud data, laser scan, and more. And again, with the help of Simulink coder and embedded coder, you can automatically generate the C++ code and deploy it onto the hardware. Not only ROS Toolbox support model-based designing, but it also enables you to connect to a live ROS network using our MATLAB and Simulink interface without you need to install any ROS distro on your host. Then, once your algorithm is ready, you can always deploy it onto the hardware automatically by generating the C++ standalone code that will be built onto the hardware and deployed either locally or remotely hardware available. And at last, you can do the offline analysis on the ROS back using our MATLAB interface and apps. Now let's move to the case study, where we'll deeply study how you can do model-based designing for a ground vehicle control system. So here is a typical components of an autonomous system that consists of many nodes. For this particular case study, we'll just focus on the controller node. Let me take you step by step how we adopted model-based designing into our V architecture. First, we started with requirements gathering and designing architectural designs. Once we have the architectural designs, we convert it into Simulink models that act as a ROS node. Once the model is ready, you can always deploy it onto the hardware. After that, you can do the unit testing. After that, you can always test the user's workflow and test whole system at once. Let's start with the first phase, that is requirement gathering and architecture. So in this phase, we'll mainly focus on the capturing, tracing, and managing requirements directly in the Simulink. Once you fix the requirements, you can always design the architectural design in the system composer. Once you have the designs ready, you can map your requirements directly onto the blocks. Requirements like interface control requirements, which ensures that there is a seamless flow of communication between publisher and subscriber. Then you can map your performance requirements to ensure that your algorithms meet the expected speed and accuracy. Then you can also add the logic requirements for the decision-making process. We are not limited to this. You can add all kinds of requirements directly into the Simulink interface. Let me demonstrate through a demo how you can add the requirements directly into the design model. For the demo, I'll be creating one requirement and mapping it directly to a Simulink block. And at last, we'll see the implementation status will be updated. You only need to just drag and drop the requirement to the implementation. That's all. And you can trace this later in the cycle. Now we have frozen our requirements and created the architectural design. Now it's time to move our design into designing the algorithm. In this phase, we'll mainly focus on developing our controller algorithm for the desktop simulation, keeping ROS out of the loop. We'll simulate our algorithm, find the potential issue, and fix them. After that, we will convert our controller algorithm to a ROS node, and then again test it. Let's start with the first task. Here we have a Simulink model where we have designed our controller algorithm. We just drag and drop the blocks and made this model. For this model to interact with the external simulator, we added a bunch of few more blocks that will facilitate the communication between Simulink ROS model with the external simulator. We have also included image sensor blocks and LiDAR sensor blocks. This whole system will now try to mimic a real-world scenario. As you can see, our algorithm is working fine. After that, we'll focus on converting our algorithmic logic to a ROS node. This is the model that we created in Simulink. Now we'll try to isolate our controller logic. We'll create two standalone Simulink models out of the single model. For that, we separate our controller logic into a different Simulink model and the rest into a ROS simulator model. Now, to facilitate the communication between controller and this external simulator, we will connect it with publisher and subscribers. Now we have isolated our controller logic as a ROS node. Now it's time to test it. Here is our algorithm in action. On the bottom left side, you can see we have our controller node running, and it is communicating with the external simulator. Once you are satisfied with the implementation, you can always come back to the requirement manager to update the implementation status. You can see there are a bunch of requirements. We all just need to click one thing, that logic has been implemented. And we can also generate the traceability matrix that will map our requirements with all the implementation available in the model. Here is a demo for that. Now we have a ROS2 node running. It's time to deploy it onto a hardware. This is where we left our model last time. Now in just one click, for the Simulink model, we'll deploy the code onto the hardware. But in the background, Simulink coder will take care of few steps, like generating your C++ code, moving it to the hardware, compiling it, then running it. And when the node is up and running, it will communicate with the external simulator. Plus, you will get an additional benefit of checking the compliance with the industry standard using Model Advisor. Here's a demonstration where in just single click, I'll be deploying my ROS node onto the hardware. On the bottom left side, we have our Simulink interface from where we will deploy our node onto the top left side where we have the terminal from the hardware. As you can see, the node is now up and running and it is communicating with the external simulator. Once you deploy the node onto the hardware, you will see it interacting with a bunch of other topics, services, and actions. To comprehend this interaction between all the things, what you can use is our app called ROS2 Network Analyzer that will help you to visualize and analyze a ROS2 network. Similar to RQT graph, but it has better filtering capabilities. Now let me take you back to the deployed ROS node and talk about debugging. We have a feature called Monitor and Tune, where you can use the Simulink as a dashboard and monitor the signal that are logged onto the hardware. And from Simulink directly, you can fine-tune the parameters, and that will be updated on the hardware on the run. Here's a demo for that. It is similar to the deployment workflow, but in this time, I'll be choosing Monitor and Tune feature here. The process will be same. It will generate the C code, compile it, and deploy it onto the hardware. The only key difference is now you have the Simulink as a dashboard where you can monitor the signals from the hardware, as well as you can fine-tune the parameters that will be reflected on the hardware. So once the node is running, you can see the plot is updated with the vehicle velocity and the current pose. Not only that, we have implemented a feature to switch off the vehicle. Here we have a switch. Once I switch it off, you can see the changes in the velocity. It dropped to 0. And once I switch it again, the vehicle starts moving. When we are talking about debugging, let's see one more app, ROS Data Analyzer. This app we will be using to visualize different kinds of messages that are available on the network. We have a lot of visualizers, and in future we'll be adding more. So we are done with the node deployment part. Now it's time for unit testing. In this phase, I'll be mainly talking about how you can automate the testing and generate the report out of it. In Simulink, you can do lots of kind of automated testing, like simulation-based testing, to ensure that your model runs fine on different scenarios. You can do requirement-based testing to ensure that your implementation meets the expected behavior. Then you can generate the report once the testing is done to review it offline. This report contains the coverage analysis that will consist of both code coverage as well as branch coverage. Not only that, you can automate more kind of testing like unit testing, model in loop testing, software in loop testing, hardware in loop testing, and back-to-back testing. Let me give you a demo how you can do it in Simulink. So here I have a model. I'll open a test case. Let's just skip that. So let me now talk about testing the user workflow. So we picked a specific user workflow where user want to transition between the different modes of controller. For instance, we have autonomous mode as well as manual control mode. For that, we implemented a service server on the Simulink model that will help us to transition between these two modes. We created one more node in MATLAB to act as a service client that will make a request to the server to change between the controller modes. Here we can see it in action. So by default, model will be using autonomous controller mode. But when we send a request from the client to change it to the manual mode and then execute the script, it will send the request to the server, and we can see the changes on the controller node. Yeah, velocity drop to 0 because we are not giving any manual commands to the controller. So that concludes all the steps that we took for model-based design. Now let's wrap up the session and look at the summary and key takeaways. With the help of model-based designing, you can verify and validate your design at each step of your development lifecycle. Starting with modeling and simulation, then you can generate the code, and at last you can do automated testing and check the generated code with compliance with standard industry standards. Let us also take a look at the ROS Toolbox capabilities. ROS Toolbox enables you to connect to an external ROS network without needing any installation. Then you can deploy your algorithmic logic by converting it into standalone C++ node that can automatically be generated using Simulink. And then you can do the offline analysis using ROSBACs. Thanks a lot for listening. You can now take pictures of this QR that will take you to the awesome MATLAB Robotics repository as well as ROS examples. Thank you, everyone.